The second section in the climbing performance is rate of climb. In the previous section, we know there is angle of attack and also rate of climb regarding the climbing performance. And we already know the angle of climb, the largest angle climb can be achieved by flying at Vx, that's maximum climb angle speed, and that's by generating the largest excess thrust ratio. Okay, so for the rate of climb, now we are focusing on that, and that happens once the obstacles are cleared, and the rate of climb is about how fast the aircraft can climb to the cruise altitude and or the vertical speed. That's what the rate of climb is about. The rate of climb typically expressed as a rate of change of altitude in feet per minute. That's basically the vertical speed, and it's read from the vertical speed indicator. So in the aircraft cabin, there is such a meter, and a negative rate of climb is referred to as a rate of descent or sink rate, and is associated with a drop in altitude. So on the right hand side, this figure shows the internal structure of the vertical speed meter, and it's basically based on the pressure difference between the ambient, the height pressure, and also the pressure setting in the diaphragm. So once the pressure difference is higher or smaller, that will drive the diaphragm to move, and then will move the needles in the speed meter. Okay, so now the target is to calculate the vertical speed or rate of climb. And now we have an aircraft like this, and it's flying along the climb path. That's the velocity vector v in red, we have it. And we know the climb angle theta or gamma because we assume there's no angle of attack. And then the vertical component is Vc. So we have Vc equals dh divided by dt. That's the height change with respect to the time difference. And then Vc is actually the vertical component of the climbing airspeed, so v times sine theta. Okay, if we go back to the equation of motion and the one along the flight path, we have t minus d minus w times sine theta equals m times dv dt. Actually, w over g is m, and dv dt is acceleration. Is that right? And then we can write theta, sine theta explicit. So t minus d divided by w, that's excess thrust ratio, and then minus the simplified part that's related with the acceleration. Okay, so now we can get sine theta, plugged it back into the equation of Vc. So we have Vc equal v times the stuff in the bracket. So if again we assume it's a steady climb, then dv divided by dt, that's acceleration, is 0. So there's no acceleration, steady climb. And then the vertical speed is v times d minus t minus d divided by w, and we can see Vc is quite similar as the gamma. The difference is there is a v in front of the excess thrust ratio. Is that right? So usually a force times velocity is power. So the vertical speed is related with the ratio of power. Okay, now we have derived the rate of climb of vertical velocity on the steady climb condition, and t minus d divided by w is excess thrust to weight ratio, as we understand from the calculation of climb gradient or climb angle. V times T is a power available from the engine. We know velocity times a force is power. V times D is a power required to overcome the drag. So the excess power available, that's T times T minus D. When the thrust is greater than the drag, can be used to accelerate the aircraft in the direction of flight, so increase airspeed, or perpendicular to the direction of flight, and can be used to climb positive. In other words, this excess power can be transformed into an increase in kinetic energy or potential energy of the aircraft. As I said in the earlier, the aircraft climb can be taken as a circular motion around the center. So a vertical acceleration is required for any increase in the climb rate. So if you want to increase the climb rate, there is a vertical acceleration required. For example, during the transition from horizontal flight to climbing flight at the end of the takeoff, the application of a vertical acceleration causes the aircraft to follow a curved flight path. So the vertical acceleration is calculated by m times v squared divided by r. That's the centrifugal force, basically, or centrifugal acceleration. This vertical acceleration to deflect the aircraft flight path upwards is provided by an excess of lift compared to weight. So that's the left-hand side of the equation. And once an acceptable steady rate of climb is achieved, then all the forces are in balance. Thus, lift equals the right and the thrust equals the drag. For this condition, so we have this steady state climb. However, a component of the weight acts rearward along the flight path. The steeper the climb angle, the greater this component. So W times sine theta. If theta is larger, the climb angle is larger, then W times sine theta is grows. So that component is larger. So we need larger thrust. In a steady state climb, constant climb angle, constant climb rate, and a constant airspeed. That's a so-called steady state climb. The engine thrust is used only to overcome the drag at that speed and to combat its weight component. That's what the first equation tells us. And we know the climb angle is a function of excess thrust over drag. And the rate of climb depends on the excess thrust power over drag power. So thrust power over drag power. And if you want to increase the climb rate, we need to increase the excess thrust power over drag power. So for given weight and throttle setting, thrust drag power available and the power required are all depend on the aircraft altitude and the speed. The airspeed for best rate of climb is named as Vy, and we already know Vx is airspeed for best climb angle. So in that case, we have at Vx we have the largest thrust over drag. Okay, so usually Vy is larger or faster than Vx, and we have a comparison here. So Vy allows us to have the quickest climb, that's Vc. Vx allows us to have the largest climb angle. So that's their definition, also compared in this graph here. Okay, just now when we talked about the Vx, we use a graphical method to help us to do the understanding. Now it's the same because we know Vc is related with thrust power minus the drag power. So we have the drag power, first of all, Vd, that's a lower curve, and the thrust power, that's a higher curve. And so if the horizontal axis is airspeed again, the vertical axis is either thrust power or drag power. So similar as the climb rate, for Vc, similar for climb angle, for the climb rate Vc, we also want the largest gap. Okay, and before we look at Vy, where the largest gap it happens, and we have VMP, so the minimum power speed. So in that case, if the aircraft is flying at VMP, minimum power, so minimum power speed, and in that case the power drag is a minimum, drag power is minimum. But that doesn't mean the thrust power, the excess thrust power is the largest. So maximum excess power available happens actually at Vy, which is larger than VMP. And we need to remember, and also Vy is larger than Vx.